Hello everyone, and welcome back to some more remote learning. In today's video, we're going to go over all the different types of asymptotes as well as introduce a new one. As mentioned in the previous worksheet, there's also a slant asymptote. So we've discussed the limit of f of x as x approaches either a positive or negative infinity, and the result is either a finite or an infinite number. When that result was a finite number, then we knew we had a horizontal asymptote. That's a line where the slope is 0. To get that horizontal line, our horizontal asymptote. However, even if that limit as x approaches positive or negative infinity is also infinite, well, we could still have an asymptote, and that does occur in some cases. However, those cases are very specific, but even though we're heading towards infinity, we're approaching some line as we head towards infinity. And obviously, it's not a horizontal line, so the slope has to be something other than 0. If the slope was 0, that's the case where we're approaching a finite number to get that horizontal asymptote. So the line it's approaching is some mx plus b, where m does not equal 0, but that slope is a real number. So as pictured below, you can see, oh, well, as x approaches infinity, our function, let's call this function f of x, also approaches infinity. But note, as it's going towards infinity, we're getting closer and closer to this line. That is a slant asymptote, and we're going to talk about the cases that occurs. So slant asymptote occurs, just like with vertical and horizontal asymptotes, when we have rational functions. However, for a slant asymptote, the degree of the numerator and denominator are very specific. In order to have a slant asymptote, the degree of the numerator is 1 more than the degree of the denominator. So if my highest degree in my numerator was 4, in order to have a slant asymptote, then the degree of the denominator would need to be 3. If my denominator had a degree of 2, well, that means that my numerator has to be 1 more, so my numerator would have to be a degree of 3. Whenever that's the case, when the numerator is 1 degree higher than the denominator, we have a slant asymptote. So I'm going to make a note of that. So again, that's when the largest degree of the numerator is 1 more than the largest degree of the denominator. So the limit as x approaches either that positive or negative infinity of our function, assuming that it's a rational function where the degrees match this statement, then we're going to approach some mx plus b. We're going to approach some line as x goes towards infinity. And obviously, when we take the limit of this as x goes towards infinity, that's also going to go towards either a positive or negative infinity, but we're hugging that line. So for the slant asymptote, the overall limit is still going to be a positive or a negative infinity. It's just the fact that we now are tracking along some line. And that line, that slope, obviously, like I stated before, is not equal to 0 because that would just be that horizontal asymptote. Now, pictured to my left, I have some function that is x squared plus 3x minus 1 all over x plus 1. So you can see that I do have a slant asymptote as I take the limit of this as x approaches infinity, because my degree of my numerator is 2, and that's 1 more than my degree of my denominator, which is 1. So what is the limit of f of x as x approaches, let's do a positive infinity? Well, use the knowledge from that previous worksheet we just did with rational functions. Our degree of the numerator is higher than the degree of the denominator, meaning our numerator is growing faster and heading towards infinity. So overall, our function is going towards infinity as x goes towards infinity. So that's the limit, but I want to figure out that slant asymptote. What is that mx plus b that we're tracking? And again, we're still taking the limit of that mx plus b, so it might even be better to write this as m times the limit of x as x goes towards either positive or negative infinity plus some constant b. we know that this is either going to go towards a positive or negative infinity, depending on the sign of our slope, and whether we're heading towards positive or negative infinity, and this constant does not come into play in the long run or towards the tail of the function, but our overall limit is still going to equal positive or negative infinity. We're just trying to figure out what line it's following along. And how do you do that? Well, we're going to start with some polynomial long division. So we're going to take that x squared plus 3x minus 1 and divide it by x plus 1. And this is going to help us get our slant asymptote. So we ask ourselves, how many times does x go into x squared? Well, that's x times. So we'll have x, and then multiplying that x through to x plus 1, that's x squared plus x. And that gets subtracted. So all I did here was take the x and multiply it by x plus 1 to get x squared plus x. And I'm subtracting that entire term. If you need a review of polynomial long division, I have a video on that, so feel free to take a look. So x squared minus x squared gives me 0. 3x minus x, because I'm subtracting that binomial, it's going to be 2x, and then I still have this negative 1 if I was to bring it down. Well, x goes into 2x a total of 2 times. So I'm going to add 2 to this and then distribute that 2 through to x plus 1. So I'm going to be subtracting 2x plus 2. So now you'll be able to see that my remainder, when I take that negative 1 and subtract 2, I get a negative 3. X does not go into negative 3, so negative 3 is my remainder. So rewriting this function, I'm going to get x plus 2 plus negative 3, so I'll subtract 3 over what I divided by, which was x plus 1. So you can see this is equivalent to my function. So if I take the limit of this, you'll see that slant asymptote. The limit of my f of x, which I'm now going to write as x plus 2 minus 3 over x plus 1, as x goes towards infinity. We know overall this goes towards infinity, but if we look at this last term, that negative 3 over x plus 1, this is going towards 0 or approaching 0. There's my line. This is my slant asymptote, x plus 2. And we can confirm that on the graph. I have a y-intercept of 2 and a slope of 1. For every 1 in the rise, I have 1 in the run. So again, let's think about the limit of a function that has a slant asymptote. The limit of that function is going to go towards positive or negative infinity because the degree of the numerator is higher than the degree of the denominator. However, because that numerator is only 1 degree greater than the denominator, I will have a line that is my slant, or another word, oblique, asymptote, that my function follows or hugs as it approaches infinity. The overall limit is still infinity, but I'm tracking or hugging along a given line. That's my slant asymptote. And how do I figure that slant asymptote? That's just polynomial long division, and then I'll be able to see my mx plus b, because my remainder, taking the limit of that, will go to 0, so I'll be left with some mx plus b. So my slope in this case was 1, and my b was 2. So x plus 2 for that slant asymptote. So now, here are the different types of asymptotes. Let's talk about them. And we've discussed 3 types. There is the vertical asymptote, there's the horizontal, and there is the slant. And when do each of those occur? Well, let's evaluate some below and pick up on that pattern. So the limit of 5 over x minus 3 as x approaches 3, I'm going to evaluate that limit and identify any asymptotes associated with this limit. So I'm not going to try to find every single asymptote in the function. I'm just going to find the one that makes sense with the limit. So as x approaches 3, what happens in our denominator? We get 0. So because our function's undefined in our denominator, we have to ask ourselves, can we cancel it out? No, we can't, so we know that this is a vertical asymptote at x equals 3. So I'm going to write vertical asymptote, and that asymptote is x equals 3. It's that vertical line x equals 3. Now I'm going to evaluate this limit. Well, if we approached 3 from the right, our denominator is approaching 0 from positive numbers and a positive constant in our numerator over a positive number that's getting smaller and smaller or closer and closer to 0, my overall fraction is going to go towards a positive infinity. So approaching from the right, I get positive infinity, whereas if I approach from the left, I'm approaching 0 from values where my denominator is negative. So a positive over a negative, that's going to result in a negative. So this is going to go towards negative infinity. So because as I approach from the right and as I approach from the left are not the same, my limit does not exist. And if I was to ask you if there were any horizontal asymptotes associated with this, what do you think you'd do? Well, remember, horizontal or slant occur as we take the limit of our function as x approaches infinity. If we get a finite value for that, it's a horizontal asymptote, and if it fits the definition above, we could potentially have a slant. So let's look at B. If I took the limit of this function as x approached infinity, let's look at my degrees, because that's what's important in this. My degree of my numerator is the exact same as my degree in the denominator. So because my degrees are the same, recalling from that previous worksheet, we're going to take the coefficients. So this is going to be equivalent to 4/6, which 4/6 simplifies down to 2/3. So because my limit of my function as x approached infinity is equivalent to 2/3, that is my horizontal asymptote. I have a horizontal asymptote at y equals 2/3. There's my horizontal line, y equals 2/3. My slope with my x is 0, so 0x plus 2/3 gives me that y equals 2/3. Now here we have x approaching infinity again. So in this case, I'm going to be looking for either a horizontal asymptote or a slant asymptote. This function actually has a vertical asymptote as well because I have some stuff in the denominator that won't cancel out, but I want that associated asymptote with the limit. So if I'm looking at it as x approaches infinity, then I'm looking for a horizontal or a slant asymptote. I know it's not a horizontal asymptote because my degree of my numerator is greater than my degree of the denominator. So as I take the limit of this, my numerator is growing faster, so I'm going towards infinity. I don't get a finite value. I know for a fact it's not a horizontal asymptote. However, my degree of my numerator is 1 more than my degree of my denominator, so it's a slant asymptote. Let's go ahead and solve for that slant asymptote. That equation we're going to find by polynomial long division. So I'm going to have x to the 4th plus 5x all divided by my denominator of x cubed. X cubed goes into x to the 4th. How many times? Well, that's x times. So x times x cubed is indeed x to the 4th, and that's what I'm subtracting. X to the 4th minus x to the 4th goes to 0, and I'll be left with 5x when I bring that down. How many times does x cubed go into 5x? Well, it doesn't. So my remainder is 5x. So this equivalent function would be, and I'll go ahead and write the limit of it since we're taking the limit, it would be x plus 5x, that remainder, over x cubed. But what exactly is my slant asymptote? It might be easier to see if I do a little bit of simplifying. If I take that 5x over x cubed and simplify it down, I'm going to have 5 over x squared. So if you can envision taking the limit of that, this is going to approach 0. So my slant asymptote in this case is just going to be y equals x. In this case, I have no b with my slant asymptote line. And if you wanted to, just thinking about this problem, you could have simplified down before we even started, because my numerator has an x in common, so I could have pulled out that x at the beginning to get x cubed plus 5 all over x cubed. When I simplify that down, my x cancels out with one of my x's in my denominator to leave me with x squared. My degree is still one less in my denominator than it is in my numerator, so because my numerator has a degree that's one more than my denominator, I would still do polynomial long division here. I would get the same result. So sometimes it's helpful to simplify first because it's a little less work, but there we have it. My slant asymptote is y equals x. So now that we kind of understand each of these, and because we've done an example of each of these all together, let's just review them and think about them in broader terms. So a vertical asymptote occurs when the limit of f of x as x approaches what? Well, think about that. If we have a vertical asymptote, we're approaching some finite value in the x. So this is going to be the limit of f of x as x approaches some finite value a, and that is going to equal, well, it's going to either be a positive infinity or it's going to be a negative infinity. So a vertical asymptote occurs when we're approaching a finite value in the x and our function approaches an infinite value. And that vertical asymptote would be x equals a. That's the line, x equals a. Now let's talk about our horizontal asymptote. Our horizontal asymptote, we're going to take the limit of f of x as x goes towards infinity or negative infinity. So x is going to approach some infinite number, positive or negative infinity, some arbitrarily large number, either positive or negative. But we want that to equal some finite value so that we can get that horizontal asymptote. So if this equals L, well then we know our horizontal asymptote is y equals L. And a slant asymptote, again, we're taking x as we approach positive infinity or as we approach negative infinity. So this is as x approaches positive or negative infinity. That's going to equal, well, it's going to equal positive or negative infinity. But this doesn't define whether we have a slant asymptote or not. We also have to note that the numerator degree, so I'm going to write numerator, is one more than the denominator. And as long as that's the case, then we're going to get some line y equals mx plus b. That is going to be our slant asymptote. And again, remember, m is not going to be 0 because if it was, that would just be some horizontal asymptote. So that's all of our asymptotes that we're going to go over in this series, all lined up together just so you can visualize the differences between each. So in example 2, we're just going to state what type of asymptote that the following functions have, but we're not going to actually solve for them. So if you realize that one of them has a slant asymptote, don't worry about doing that polynomial long division for it. So let's just go in order just to keep this simple. Let's first check for any vertical asymptote. And a vertical asymptote occurs when that denominator cannot be canceled out. So in this case, can we factor and then cancel out this x minus 3? No. Even factoring our numerator, that would be x times x minus 2, which does not leave us an x minus 3 that we can cancel out. So we know we do indeed have a vertical asymptote. So I'm going to write VA for vertical asymptote. And let's just talk about it. Where would that vertical asymptote be? That would be at x equals 3. So our next question is, do we have a horizontal asymptote? And that's when we take the limit of the function as x goes towards either infinity or negative infinity, and we get a finite value. Well, if we think about the limit of this, our degree in our numerator is higher than the degree of the denominator. So if we're going towards infinity or negative infinity, our limit will also be equivalent to infinity or negative infinity. So we do not have a horizontal asymptote. However, check this out. Our degree in our numerator, that highest degree, is exactly one more than our degree in our denominator, so we know we do indeed have a slant asymptote. So in A, we have a vertical asymptote and a slant asymptote. And remember the way you would solve for a slant, you would do that polynomial long division and get that y equals mx plus b. Now, moving on to B, I have some function g of x. So my first question I'm going to ask myself is, do I have a vertical asymptote? So in my denominator, what would make this 0? Well, there's no number that would ever make this 0, because even if this was a negative squared, it still becomes a positive, and we're adding to it. This function is defined for all real values of x. We're never going to have a vertical asymptote. So, no vertical asymptote. What about a horizontal asymptote? Well, our numerator has a higher degree than our denominator, so as we go towards either positive or negative infinity, g of x is also going to approach positive or negative infinity. So we don't have a horizontal asymptote. But the degree of the numerator is higher than the degree of the denominator by exactly 1, so here's the case of a slant asymptote. Now let's look at C. If I have x cubed plus 2x over x plus 5, first let's check for those vertical asymptotes. What makes my denominator 0? That's going to be when x equals negative 5. Am I able to cancel out this x plus 5? No, there's no factor in my numerator that I can cancel out that x plus 5 with, so I do indeed have a vertical asymptote, and again, that's going to occur at where my function is undefined in this case, which is x equals negative 5. Now let's talk about a horizontal asymptote. Do I have a horizontal asymptote for this? Well, my degree of my numerator is higher than my degree of my denominator, so if I take the limit of this function as x approaches some positive or negative infinity, the function will also approach positive or negative infinity. So no, I don't have a horizontal asymptote. Do I have a slant asymptote? No, I don't, because my degree is 2 more in my numerator than it is in my denominator. So for C, all I have is a vertical asymptote. Now for g of x, our function in part D, let's first check for vertical asymptotes. Two things would make this function undefined. If x was equal to negative 2, and if x was equal to negative 1. But remember, if I can cancel any of those factors out, that will not be a vertical asymptote. It would just be a hole. So let's factor g of x and then simplify down. So x squared plus 5x plus 6, what multiplies to give me 6 and adds to give me 5? That's going to be 2 and 3. So I'll have x plus 2 as one factor, multiplied by x plus 3. And remember, my denominator is x plus 2 over x plus 1. So you can see that my x plus 2 cancels out. So x equals negative 2 isn't actually a vertical asymptote. It's just going to be a hole because it canceled out. However, this x plus 1 does not cancel out, so I do still have that one vertical asymptote. So even though one of my factors canceled out, I still have one vertical asymptote in my problem, and that's when x equals negative 1. Now, because we already simplified this, why don't we just work with this simplified function? Let's take the limit of that as x approaches a positive or negative infinity. What would that be? Well, my degree of my numerator matches my degree of my denominator. They're both a degree of 1, and the coefficients of each of those is also 1. 1 divided by 1 is 1. So I have a horizontal asymptote at y equals 1. So I have a horizontal asymptote, and I also want to note that because those degrees are the same, I know for a fact I don't have a slant asymptote. So this is how you want to think about these different types of asymptotes. And understanding these asymptotes is really helpful for when you're trying to visualize a function. And it's also great limit practice. So now that you've done quite a few examples and practice problems, if you still need more, feel free to go to the textbook or an online resource to get more practice problems. And once you get comfortable with this, continue on to the next video. But for now, good luck with your online learning.